Welcome back, everybody. I'm Jeff Bier, founder of the Embedded Vision Alliance and president of BDTI. As I mentioned earlier this morning, my colleagues and I started the Embedded Vision Alliance about 2 years ago because we were and we are really excited about the potential for embedded vision technology now that it's becoming feasible to put embedded vision technology into almost any kind of product. In this presentation, I want to share with you some of what has fueled my excitement about the technology, especially some examples of some of what I consider to be the coolest, most impactful products out or coming out harnessing embedded vision. I also want to share a few thoughts about what may be coming next through the efforts of product creators like yourselves. And at the same time, I'll highlight some of the very real challenges that exist. This stuff is not simple, as well as some of the, let's say, hopeful trends that we see that are increasing our ability to overcome those challenges. This is probably redundant for almost everyone here, but just to make sure we're all on the same page, let me say that by computer vision, we mean systems that extract meaning from images. There are lots of systems that process images without extracting meaning. They may capture, compress, store, transmit, enhance the appearance of images, but they don't care about what those images represent. That's not what we're talking about today. What we're talking about today is machines where the main focus is trying to understand something about the world through those visual inputs. One really interesting observation that I read recently from neuroscience is that approximately half of the human brain is dedicated to vision. That's, to me, a really interesting fact. And although I'm no neuroscientist, I take two inferences away from that. One is half of the human brain is a lot. That must mean that vision is important from a biological point of view. Evolution has allocated a lot of resources to it. And evolution tends to be pretty efficient about allocating resources, right? We have 2 legs for a reason as opposed to 3 or 8. So evolution has allocated a lot of resources to vision. And secondly, apparently it takes a lot of resources to do vision because half of our brain, it's a lot of neurons dedicated to vision. I think those are some interesting ideas to carry forward when we think about implementing visual intelligence in machines. We use this term embedded vision. We certainly didn't invent the term, but we've adopted the term embedded vision as distinct from computer vision to kind of signal the transition from computer vision as a niche, exotic, often temperamental, expensive technology to one that is rapidly becoming ubiquitous. And so what we mean by embedded vision is the practical deployment of computer vision in all kinds of systems and applications, whether those systems be typical embedded systems or mobile devices or the cloud or something else. That doesn't really concern us terribly in terms of the definition. We don't mean by embedded vision to limit it to embedded systems. We really mean by embedded vision to signal this transition that we see happening from niche exotic technology to ubiquitous technology. And that's really what we think is new and exciting here. Computer vision's not new, of course. Some people trace its origins to the early days of the US space program in the 1950s. Even embedded vision in a more literal sense of the term is not new. There are expensive military weapon systems and factory automation equipment and so on that have been for decades that incorporate vision in an embedded manner. But those have tended to be rather expensive, exotic applications. What is different now is that it's becoming possible to incorporate vision into almost anything, into literally a $100 consumer product that sits in your pocket and is the size of a pen, for example. And that, we think, is really exciting and offers a lot of potential for product developers to create new kinds of products and to meaningfully enhance the capabilities of current existing products. Now, what is fueling this transition, you probably won't be surprised to hear, is improvements in, first and foremost, the hardware. Generally speaking, a vision system requires at an absolute minimum a sensor and a processor, and a lot of processing power. To be able to achieve that level of processing power and have sufficient signal quality from the sensor to be able to do robust vision, and do it in a system that has serious size and cost and power constraints, we're just now getting to the point of being able to do that. And I'll show you some data in a minute to support that assertion. So underlying hardware improvements, especially in processors and sensors, are, I think, the biggest factor making this possible. But it's also about improvements in algorithms. And we just heard some really interesting algorithm work in Peter Bier's talk from his work in robotics as an example of that. So improvements in algorithms are also key. And not only algorithms, but also APIs, software libraries, know-how, techniques, and so on. This is all important elements to enabling people to incorporate vision in products. And these are all things that have improved remarkably in the last few years. Going back to processors for a minute, here's some data to back up my assertion about processors. My company, BDTI, does a lot of benchmarking and evaluation of processors, as well as a lot of optimized embedded software development. So we're very close to processor performance. And I've chosen here Texas Instruments high-end DSPs simply because that's one of the classes of processors that we have the best historical data on going back many years. And what I've plotted here is, just in very simple terms, using multiply accumulates per second, the performance that you could get out of a single core high-end TI DSP over the last roughly 10 years. And I've also shown a horizontal line here. It's a somewhat arbitrary, but I think appropriate threshold of 10 billion multiply accumulate operations per second. 10 billion multiply accumulate operations per second is a fairly typical requirement for a vision application. Some are much lower, some are much higher. Of course, it depends on exactly what you're trying to do. But usually we're talking about tens of billions of operations per second. And what you can see here is that taking this particular family of processors from TI, which is clearly optimized for delivering a lot of performance on these kinds of streaming digital signal processing problems, which include a lot of image and video and vision kinds of algorithms. They crossed the 10 billion multiply accumulates per second threshold in 2008, so just a few years ago. And if we plot similar curves for other classes of embedded processors, we see similar kinds of curves, similar crossing points. So this is just one example, just one type of processor, just one instance of that type, but it helps to make it concrete. You know, why are we seeing these products proliferate now and we didn't see them 5 years ago or 10 years ago? And I think it's largely because of exactly what you see here. Of course, those trends are also evident in the sensors. I think the sensors have benefited enormously, low-cost sensors have benefited enormously from mobile phones, right? Every mobile phone has lots and lots of sensors in it, especially including image sensors, usually a couple of image sensors. It's a super high volume product, very cost sensitive, very power sensitive, very size constrained. And so now the sensors have made huge advances in terms of what you can get in a very tiny space for a very modest amount of power for a very modest amount of money. So you combine the processor and the sensor, and then you add software, right? And depending on the software that you add, you can make that thing do a lot of different things, right? It can be a gesture recognizer. It can be a roadway, road hazard monitor. It can be some kind of quality control inspection system. It can be a lot of different things depending on what software you run on. And I think this idea of a software-defined sensor, kind of in the spirit of software-defined radio, is a useful way to think about how vision is typically implemented. For example, one conclusion it leads to is, well, even if a system wasn't originally designed with vision in mind, we might be able to retrofit it. If it has this kind of basic architecture, we might be able to retrofit vision capabilities onto it. And in fact, that is exactly what we see happening today with mobile phones. You have a mobile phone, a smartphone, a tablet, it has a sensor, image sensor, it has a very powerful processor, and even though it wasn't certainly I know mine wasn't designed with computer vision in mind. It didn't come from the factory with any computer vision capabilities. Nevertheless, there are now thousands of applications I can download on it to do things like monitor my health and help me stay safe on the road, help me navigate around a foreign city, et cetera, by adding software to this basic platform. So I think that's a useful way to think about some of these, sort of what we can do with some of these vision capabilities. What we can do with vision capabilities is really extremely broad. And I try to sort of think about it at the top level. What are the kind of classes of things we can do? And to me, the biggest, most important classes are these kinds of things. Like we can improve efficiency of lots of different things, not just factory production lines, but retail store, supermarket queues and keeping the shelves stocked and so on. We can enhance safety for sure in the automotive application, which I'm going to talk about in a bit. And that's, I think, like I said earlier this morning, one of the quite possibly fastest maturing embedded vision applications, but not only in cars, also in swimming pools and in various kinds of industrial situations, in schools and so on. We can simplify usability. I'm going to show you a video clip in a few minutes, a kind of visionary video clip from Microsoft that illustrates some of these ideas. But I think simplifying usability is a huge potential here, not just for personal electronic devices and game consoles, but for all kinds of complex technology systems that today are confusing to the average user, difficult to use, therefore they avoid using them or they don't use them well, and they don't get the value they could out of them. And then maybe the broadest and most exciting category is this last sort of catch-all one, which is, well, what kind of new thing can you create? One of my favorite examples of this is the Live Scribe Smart Pen, which is a pen just slightly larger than a typical pen that has a camera built into the tip, an infrared camera. It writes on special paper, and the infrared camera tracks the just barely visible dot patterns that are encoded on that special paper. And by doing so, of course, it can record all the pen strokes, which means it can later you can upload your sketches and your notes to your personal device or the web. But also, it can uniquely identify any page and any point on any page. And it has an audio recorder. So if you're a student, let's say, sitting in lectures, taking notes, you can record the audio while you take your notes. And then when it's finals time and you're cramming, and you're looking at the notes from 6 weeks ago and you're trying to figure out, what did I mean here? What did the professor mean? You tap the pen at that point on your notes, and you immediately hear the audio recording from the moment you made those particular notes. It's a really brilliant idea. It's a pretty popular, successful product. It's the kind of thing that would be very, very difficult to do if you didn't have the ability to embed computer vision in it. And I think there are thousands of such things waiting to be invented. One of the things I find really interesting about computer vision, there are many paradoxes, in my opinion, in computer vision and embedded vision. One of them I started thinking about after I had a chat with Professor Jitendra Malik from UC Berkeley a couple of years ago. Professor Malik has had a long and distinguished career in computer vision, and I asked him sort of, big picture, what are your takeaways from 30 years doing this? And he said something that struck me as funny at the time, which was, well, what really irks me is every time I go to a family event or I go to a social event and people ask me about what I do, and I explain what computer vision is, they're like, oh, well, why is that big deal? It's effortless for people to pick out the unripe tomato from the batch or see that you're following too close to the car in front of you. Why is that a subject for rigorous academic research to make machines do that? So it's interesting that we take it for granted, we take vision for granted because it's effortless for humans. Algorithmically, we often struggle to reproduce even a small subset of human visual capabilities in an embedded vision system. And it is, we have a sort of daunting bar to reach in many cases to match what human vision can do. Yet, on the other hand, there are plenty of examples today, and I'll show you a couple of them, of vision systems, even low-cost vision systems, that far exceed the capabilities of what human vision can do. And so that's, to me, a very interesting paradox. On the one hand, we often struggle to approach what human vision can do technologically. On the other hand, in other cases, we readily exceed what human vision can do. And I think due to the increased improvements in these underlying technologies that I mentioned earlier, the processors, the sensors, the algorithms, et cetera. More and more, we're going to be able to raise the bar and come closer and closer to what human vision can do, and in more and more cases, even exceed what human vision can do. What does make vision hard from a technological, from an algorithm point of view? Well, to me, I think the thing that makes it hardest is that many of these applications have just completely unconstrained inputs. The classical factory inspection computer vision application is, beer bottles going down an assembly line, and that's a very constrained, controlled situation. Right? We can control the lighting, we can control the geometry of the arrangement of the camera with respect to the bottles going by. We know exactly what we're looking for, what a correctly assembled bottle with label and cap looks like. And so it's very easy to detect variances from that. That's fantastic. But then compare that with this kind of thing, a camera looking through a windshield at a road scene. There's no constraint. You could see anything out that window. And you do, right? If you live long enough, certainly if you drive around here, eventually you will see everything. Not only that, the image quality is subject to huge variation because your windshield can be dirty, it can be raining, you can have glare, like in this scene. So it's really challenging to then create a system that can take these images of highly varying quality, of unconstrained construction, and then reliably make some decisions about what does this mean, right? And certainly in the case of something like automotive safety, it better be reliable. One of the things that made me realize that embedded vision is real was a couple years ago when Mercedes started shipping the active vision-based safety system, the one that actually will apply full emergency braking at highway speeds. And knowing what I do know about vision, at first I thought these people are crazy. They have this beautiful, highly valued brand, and they're going to blow it now because they're going to cause an accident somewhere by this system having a false trigger, and it's going to be a disaster for them. But it turns out the system is rock solid. They've done their homework. It's not purely vision-based, and that's part of how they make it rock solid, right? They combine vision with radar or other technologies to get a really, really robust solution, so they know that the car isn't going to spontaneously apply emergency braking for no good reason in a highway situation where it could very well cause a serious accident. One of the things that makes vision really hard compared to some other fields where we have similar kinds of algorithms and processes like video compression or wireless transmission is that we really lack analytical models in vision the way we have in something like video compression or wireless baseband. When we're designing the next wireless baseband standard, we have really pretty reliable models for how wireless signals propagate. And based on that, we can mathematically derive, given the various constraints we're operating under, what is the optimal modulation scheme? And people skilled in the art more or less agree, okay, this time it's going to be this flavor of CDMA, and off we go. With vision, it doesn't tend to work that way because we usually don't have these models. And so it becomes much more of an experimental field where people try stuff. And it works in the lab, and then they take it out into the field, and it doesn't work. And they examine why it didn't work and tweak it and then repeat that cycle infinitely. And a good example of this is in this kind of automotive safety application, there's an Israeli company called Mobileye, which is arguably the technology leader in this space. Mobileye claims to have about 500 man-years invested in algorithm development for automotive safety applications. And that's probably a legitimate number. I know they've been doing this for over 10 years. They've been publishing papers, and they have a sizable team working on it. Well, I have a Mobileye system in my car. I put one in about 2 years ago. They sell an aftermarket product that you can add to any car. And I can tell you that while it works pretty well, they're not done. I do get false alarms, usually once or twice a day, and that's a very problematic situation with a system like this because you learn to ignore the alarm. Instead of reacting right away, you learn to filter and say, it's probably a false alarm, let me look around. And of course, if it's not a false alarm, you lose very, very precious time that you could be using to react to a hazardous situation. So they've got 500 man-years plus or minus in it, and they're not done. And that's kind of typical of these applications where you have these very unconstrained inputs. I don't know that we're ever going to be done with these kinds of problems. We can get to a place that it's good enough to deploy, but there's going to continue to be opportunities to improve. So these are some of the things that I think make vision hard kind of at the algorithmic level. And then when we talk about, well, putting a system together, the implementation level, there's another set of challenges. One stems from the fact that these systems are kind of multidisciplinary, right? By nature, they involve sensors and optics and sometimes lighting and processors and algorithms and so on and so forth. And rarely does one person or one product development group have all of the required expertise. And as with most kinds of systems, the system's only as good as the weakest link. So if you've chosen the wrong sensor, no matter how powerful your processor and good your algorithm, you're probably not going to recover from that bad choice of a sensor, for example. So this is a challenge, I think, for the industry, is that very few organizations outside of the places that have been doing computer vision for decades, like Lockheed Martin and so forth, have the full spectrum of expertise. It's going to need to be developed. It's going to need to be diffused throughout the industry. Second, performance requirements tend to be really high. I talked about tens of billions of operations per second because A, we've got a lot of data, billions, millions, hundreds of millions, sometimes billions of items of data per second coming in from video sensors. And then we're applying non-trivial algorithms to them because it takes non-trivial algorithms to extract meaning from these scenes. So high data rates times complex algorithms obviously yields high performance requirements, which is not such a big deal if you're in an unconstrained environment where you can just keep throwing high performance CPUs, fill out racks of equipment, fine. But of course, in many environments, that's not practical. You have a very constrained budget for size, for cost, for power consumption. So how do you get that billions, tens of billions of operations per second of performance in that very constrained cost, size, and power envelope? That's a big challenge. And usually it implies a need for careful optimization of the algorithm implementation on the processor so that the algorithm implementation is making good use of the processor. It also often implies the use of heterogeneous processors or specialized processors of some kind. General purpose CPUs have the advantage of being really easy to program. They have the advantage of having lots of software libraries available for them and so forth. And they have tons of performance. But when you look at the performance per watt, per dollar, per cubic inch, that's where they tend to fall short, and that's why we often wind up in embedded vision applications moving things away from a general purpose CPU into some kind of specialized processor or coprocessor, or maybe several of them. And that's how, for example, in a mobile phone, that's how you get the kind of amazing video playback and 3D graphics in other application domains. It's not because you have a 1.5 gigahertz quad-core CPU. It's because you have these various, very specialized, very, very efficient accelerators and coprocessors working in concert with the CPU. And that's going to be the case in many embedded applications as well, whether it be a GPU, a DSP, an FPGA, or some other kind of specialized processor. The good news is those processors exist, and throughout the day today, we're going to hear a number of presentations about how to use them for various of these applications. The bad news is when you step away from the CPU into some kind of specialized, possibly heterogeneous architecture, your programming complexity goes way up. You have to know a lot more about the architecture. The tools aren't as good. It's just a more complex process and processor. And then your software becomes immediately much, much less portable in most cases. So your ability to move it from one processor to the next, vendor A to vendor B, or generation 1 to generation 2 is much more limited. As I said earlier, there's also the fact that most kinds of products haven't been able to afford, so to speak, computer vision capabilities means that most companies building most kinds of products don't have that expertise. So that's another obstacle. So let me show you a few examples of products now that I think are particularly impactful and, to me, inspiring in terms of what's possible with embedded vision. Perhaps predictably, I'll start with the Microsoft Kinect, which I think has had a number of really big impacts. I'm going to show you a video from Microsoft. You probably will miss the little disclaimer that flashes by at the bottom of the screen for about a second. So I'll tell you what it says. The disclaimer essentially says most of what they're showing here is not within the actual capability of the current product. It's more aspirational. Nevertheless, I think it's a very interesting video. So let me show it to you and then talk a little bit more about the...
We started with a sensor that turned voice and movement into into magic.
Xbox, play.
And we thought, this will be fun to play with. And it was. But something amazing is happening. The world is starting to imagine things we hadn't even thought of. Unexpected things. Helpful things. Beautiful things. Inspired things. Which is why, even though the world keeps asking us what we'll do with Connect next, we're just as excited to ask the world the same thing.
I think Microsoft deserves enormous credit for very successfully executing the Kinect, well before anyone else has delivered something comparable. It should be said that when they show things like playing a virtual violin, that can't actually be done with the current generation Kinect. It doesn't have that kind of resolution to resolve fine finger movements. It's more for gross, large-scale gestures like you would use for swatting a virtual volleyball or something like that. Nevertheless, I think it is appropriately kind of aspirational, inspirational to think about, well, what can we do in the next generation when we do have better resolution? And I think the Kinect has had some really important impacts in 3 areas. One is Microsoft has sold 24 million of these things in the last couple of years since they've introduced them. I would be hard-pressed to think of any other vision system that has shipped anywhere near 24 million units. So many consumers have had, will have their first experience with vision technology thanks to Microsoft via the Kinect. So that's pretty cool. They're introducing consumers to what's possible with vision on a large scale. Secondly, following immediately from that volume number, Microsoft has shown that vision and even 3D vision, which had been thought of as a pretty expensive, exotic technology, can be a high volume consumer technology, and therefore can be a big business. And that has spurred incredible surge of investment in low-cost 3D sensors in the last few years. I was at CES in January, and I must have seen 8 new low-cost 3D sensors. Amazing. And 3D sensors are really powerful. You can do certain things a lot more easily with a 3D sensor than with a 2D sensor in terms of the complexity of the algorithms and the amount of the computation required. So if you can get an inexpensive, low-power, small 3D sensor, and now you can, I think we're going to see 3D sensors being very common, and the Kinect is just the first example of that. And then finally, and perhaps in the long term, most importantly, by making this inexpensive peripheral available, Microsoft has empowered thousands of engineers to experiment with vision, especially with 3D vision. Hobbyists, students, but also researchers in industry and product developers in industry are using the Kinect to develop and prototype products and experiment with new techniques because it's very inexpensive, it's very accessible, the APIs are documented and so on, and there's a whole big community of people using it. So there are people you can go to when you have questions. Gary Bradsky, who's speaking next door, is an esteemed technologist in computer vision and in robot perception. When I went to visit his lab at Willow Garage 2 years ago, those PR2 robots that you saw in Peter Abeel's talk, the 2-armed robots, half of them in Gary's lab had Kinect sticking out of their heads. I said to him, Gary, what is going on here? You're Mr. Robot Vision. You have your custom designed stereo vision system for these robots. Why are you using the Kinect? And he said, in essence, it's $100. We can't make a cup of coffee around here for $100. Ours is better, but it's 50x the cost. For $100, we'll use it and we'll compensate elsewhere, for its shortcomings. I thought that was pretty interesting, especially coming from him. So let me show you an example of some of what the Kinect has inspired. This is a video from the Human Computer Interface Group at the University of Konstanz in Germany. And ignore the fashion-forward aspect of it for a minute. Just Pay attention to the functionality. These are just students who've done this as a class project.
Turn right.
That's the debugging console in the back.
Walk forward until the next information appears. Keep left. Attention. Obstacles on left side.
So what this system is doing is it's using the Kinect, both the depth sensor and the 2D visible spectrum sensor to the depth sensor to map the contours of the space, and the 2D sensor to look at these QR code type markers. And so it gives these two sources of information. It has the depth map, so it knows what the room contours look like, and then it can essentially read signs that have been put there for that purpose. And then it gives information to the user both through speech synthesis, through the Bluetooth headset, and also this belt that he's wearing has a set of piezoelectric vibrators in it. So it vibrates on a certain side to signal that you're approaching, let's say, a wall. To me, I mean, this is a really powerful concept to think that, you know, people who are sight impaired may be able to, at some point, you know, have a little contraption on their glasses, for example, and an earphone, and navigate much more autonomously. It's a really quite powerful and inspiring idea. And you know, we owe thanks to Microsoft for empowering people to do thousands and thousands of experiments like this with the Kinect. You know, the Kinect is a gesture control device. And one of the things I find interesting about this is we tend to talk about gesture as if it's one thing, but actually it's many different things. And that's often the case in these different areas of vision functionality. It's not really one thing. So for example, you know, is a gesture a small hand movement like this, like a wave? I might wave to a friend across a room. That's kind of on the edge of what the current Kinect can do. The current Kinect can't resolve small hand gestures like thumbs up or okay, for example, but those are also gestures, right? The current Kinect is more about gross body movements, you know, waving the arms, moving the torso, jumping up and down, and so on. So that's clearly a kind of gesture, and it can be a single user or it can be a multi-user scenario. So those are different kind of use cases. Then we get into the fine finger movements, like in the Microsoft video, playing a virtual violin or guitar. I would consider that also to be gesture. It's a different kind, different flavor of gesture again. What about facing something? If I turn my face towards something, is that a gesture? I think so. Certainly people pick up a lot of information by observing in a room where people are facing. And you take that to the next step, what about where people are looking, where their eyes are looking? Well, they get a lot of information about that, right? When you come into a room and you see where people are looking or you're talking to somebody. So I consider that also to be under the umbrella of gesture. And then finally, what emotion am I expressing? Is that a gesture? Definitely in my house. This isn't my little girl, but I have two, not too different from her, and I get a lot of information from facial expressions in my household. So I would contend that these are all different classes of gesture, and it's a little bit dangerous to talk about gesture as if it's one thing. What are we trying to do? If we think gesture is only this sort of thing, then we're limiting ourselves severely in what we can do. If we contemplate this whole range, and I'm sure there are other cases that I haven't imagined here, then we have a much bigger universe of things that we can accomplish with gesture. And here's an example of that. This is a demo. I don't actually have a video of the demo here, but you can actually run it online from a startup, an MIT spin-out called Affectiva. Affectiva's product is called the AFDEX system, and the AFDEX system reads people's emotions using vision algorithms. Currently, it's a web-based system used for market research, and you can run their demo, go to their website, they'll show you some TV commercials with your webcam watching your face, and they track, I think, 5 or 6 different dimensions of your emotional state, second by second, as you watch the TV commercial. You can see the plot here on the bottom of the slide, and then assess from that, what did you think about the commercial overall? Which portions did you find particularly interesting? Which portions did you find boring? Which were surprising? And so on. as you can imagine, market researchers basically kill for this information, right? The closest they can come today with previous generation technology is have people fill out questionnaires. And that's notoriously unreliable. People don't even necessarily know how they reacted to the thing while it was happening, and then when they come to fill out the questionnaire, they're just as likely to tell you what they think you want to know, what they think you want to hear, as opposed to how they actually felt about it. So this way, you take the middleman out, so to speak, and you just read directly from the person's affect, from their facial expressions, how they feel about it. So this has huge potential, not only market research. And this is a really pretty hard problem, right? If you think about it, it's one of these things where people do it pretty effortlessly. Machines, it's hard. It's hard to figure out how to reliably do this. You get all kinds of situations with facial hair and eyeglasses and so on, and you need this to be robust if it's across a wide population, different lighting conditions, people aren't going to be holding perfectly still, et cetera. You need it to work robustly across all these conditions. So this is one of those cases where getting the machine to do something that's effortless for humans is really a pretty monumental effort. But I think Affectiva is well on its way to getting that done. Here's a case where another company has actually gone well beyond what humans can do. This is a commercially available app for iOS devices with a front-facing camera from Philips. It's called Philips Vital Signs Camera. Let's watch the video. Do we have?
Hi, I've recently downloaded an amazing new app from Philips called Vital Signs Camera. The Philips Vital Signs Camera app measures your heart rate and your breathing rate just by using the camera on your iPad 2. To get a good measurement, you have to go and place the iPad on the table. So come with me, let's see how it works. So here I am at the table, and there's the Philips Vital Signs app. So as soon as I open it up, it starts to work automatically. I just have to make sure that I keep my face inside the marked areas on the screen. And I also have to sit still and quiet during the measurement. So now it's finished and I have my results. My heart rate is 60 beats per minute and my breathing rate is 14. So I'm happy with that.
This thing works. I have it on my iPad. It actually works. You need decent lighting conditions. You need to not be moving around too much, but it does work, and it's great for cocktail parties because non-technical people are like, wow, that's cool. Engineers are like, no way. How does that work? Turns out your skin tone changes as the blood flows. And so even with the limited sensor in the mobile device, with the right algorithms, they can pretty reliably detect the heart rate. Automotive safety is, I think, a really compelling application. When I was doing some research on this a year or so ago, I learned that over 1 million people a year die in automobile accidents. Really astounding. It's the second leading cause, it is the leading cause of accidental childhood death in the US, for example. I think we can do better. Apparently Mercedes agrees. Let me just show you one more if you want to think about going beyond human visual capabilities. This is a mosquito. This mosquito is about to be exterminated by a laser pulse steered by computer vision. This is a project of intellectual ventures responding to a challenge from the Gates Foundation, which, as you may know, has one of its projects trying to eliminate malaria, which kills millions of people every year in the undeveloped world. There he goes. I should say, there she goes, because it distinguishes between male and female mosquitoes. It only shoots down the female mosquitoes because they're the only ones that bite. It also doesn't shoot down other kinds of insects. It only is interested in female mosquitoes. So, as an example of going beyond what human vision can do and enabling new kinds of capabilities, wow, really impressive. So I've got some other examples, but I'm also out of time. So let me skip to the conclusions. And I'll be happy to share my other examples. I usually carry a bag of demos around with me wherever I go, so feel free to stop me in the hallway if you want to see more. And also, you come to the Embedded Vision Alliance website, where we have tons of videos of very inspirational and impactful vision products and proofs of concept, like the mosquito zapper. So to date, computer vision's largely been a niche, expensive, temperamental technology. That is now changing very rapidly for the reasons that I've explained, thanks first and foremost to improvements in the hardware, low cost, high performance, energy efficient processors and sensors. And there's so much we can do with this. Vision upgrades what systems know about the world around them. I think that's the most general, most succinct way of summarizing it. And by upgrading what systems know about the world around them, those systems can be much more capable and responsive and accomplish much more for us. But it's not simple. We're on the edge of what's feasible, and there are lots of challenges. And one of those challenges is that most companies, most product creators who can be using vision in their products don't have experience with it. And so that's what we're working on with the Embedded Vision Alliance is, can you imagine what your next product is going to be? A faster something, a more efficient something, a safer something. And if you can, we want to help you bring that vision, so to speak, into reality by helping you understand how the technology works, what the trade-offs are, network with experienced engineers, connect with the right suppliers. So please come make use of the Embedded Vision Alliance website. Come see our member companies' demos in the demo room 238 down the hallway today, and give us your feedback. Tell us what else we can do to help you. Speaking of feedback, please fill out your evaluation forms as we go throughout the day today. That feedback's really important to us. If you're just getting started in vision, one of the easiest and funnest ways to get started is with a couple of free tools that are available for download from the Embedded Vision Alliance website. There's a OpenCV executable demo package that runs on any Windows machine with a webcam, lets you experiment with a number of basic vision algorithms. And then there's an OpenCV starter kit, as we call it, that helps you get started with embedded vision development on a PC using OpenCV, which is a very, very popular library.